Hello everyone, welcome back to CodeMaster. In today's video, we are diving deep into classic recursion problems. We will explore what recursion is, break down some common recursive problems, and go through the Python code step by step. By the end of this video, you will be confident enough to tackle recursion-based coding problems easily. Let's start with the basics. What are recursive problems? These are problems that can be solved by breaking them down into smaller identical subproblems. We solve the smaller instances, then combine the results to solve the main problem. In recursion, a function calls itself, but to avoid infinite loops, we need a base case, a condition where the recursion stops. Why use recursion? It simplifies complex problems, especially those involving trees, graphs, or nested structures. However, recursion can sometimes lead to high space complexity, so we need to be mindful of that. Let's start with a simple yet classic recursive problem, factorial of a number. The factorial of a number n is the product of all positive integers from 1 to n. The recursive formula is n factorial equal to n into n minus 1 factorial. The base case is factorial of 1 equal to 1. So for example, if the factorial of 5, we need to print the output 120 as 5 into 4 into 3 into 2 into 1 equal to 120. Time complexity is order of n and space complexity is order of n. So let's break down the code. So first we define a function called factorial that takes one parameter n. This is the base case. If n is 1, we return 1 and stop the recursion. If n is not 1, we move the recursive case. We will return n into factorial of n minus 1. We multiply n by the result of factorial of n minus 1. This keeps breaking the problems into smaller subproblems until we hit the base case. So for example, factorial of 5 is 5 into 4 into 3 into 2 into 1, which result in 120. Next, we have the Fibonacci sequence. It's a series where each number is the sum of the two preceding ones. The recursive formula is f of n equal to f of n minus 1 plus f of n minus 2. The base case is f of 0 equal to 0 and f of 1 equal to 1. For example, for f of 5, we need to print 5 elements 0, 1, 1, 2, 3 and 5. Time complexity is order of 2 raised to n and space complexity is order of n. So here's the code for Fibonacci sequence. So first we define a function named Fibonacci with one parameter n. So base case is like if n is 0 or 1, we return n. So this is the base case. If n less than or equal to 1, we will return n. In the else case, for larger values, we compute the sum of the previous two numbers. Then we return n minus 1 plus n minus 2. This is the recursive call, breaking the problem into smaller subproblems. Next comes the Tower of Hanoi problem. It is a famous recursive puzzle. The goal is to move n disk from a source node to a target node using an auxiliary node. The rules are only one disk can be moved at a time. A disk can only be placed on a larger disk or an empty node. For example, if n equal to 3, there are 7 moves. Time complexity is order of 2 raised to n and space complexity is order of n. So let's see the recursive solution. First, we define the function with n disk and 3 rows. If n equal to 1, base case, if there is only one disk, move it directly. Then we will move the top n minus 1 disk to the auxiliary row. Then we will print the move for the nth disk. Then move the n minus 1 disk from the auxiliary row to the target row. Next is the binary search. It searches for an element in an sorted array. It repeatedly divides the array in half. For example, if the array is 1, 3, 5, 7 and 9 and we need to find the target 7, the result should be 3 since 7 is present at the index 3. Time complexity is order of log n. Space complexity is also order of log n. This is the code for binary search. First we define the binary search. We will pass array, the low, the high and the target. If low greater than high, we will return -1, which is the base case. Then we will find the mid as low plus high divided by 2. If array of mid equal to target, we will return the middle value. If array of mid greater than target, we will return the binary search and array low, mid -1 and target. In the else case, we will return mid +1, high and target. This is for the left case and this is for the right case. Next, we have the string reversal. It is to reverse a given string. The approach is simple. We swap the first and last characters, then recurse on the remaining substring. For example, if the input is HELLO, we need to get the output OLLEH. Time complexity is order of n. Space complexity is also order of n. So this is the code for it. First, we define the reverse string. We will pass the string. If the length is 0, we will return s, which is the base case. In the else case, we return s of -1 plus the reverse string, the last element in it. Next, we have the permutations of a string. It generates all possible permutations of a string. For example, permutations of ABC is ABC, ACB, BAC, BCA, CAB and CBA. Time complexity is order of n factorial and space complexity is order of n. This is the code for permutation. So first, if step equal to length, we will join the string. Then for I in range step to length of s, we will copy it. S of copy equal to character for character in s. S of copy of step comma s of copy of I equal to s of copy of I comma s of copy of step. We will recursively call the permutation function. Next is tree traversal. It traverses a binary tree recursively in order, pre-order or post-order. So for example, tree with nodes 1, 2, 3, the in order is 2, 1, 3. Time complexity is order of n and space complexity is also order of n. This is the Python code for it. In order traversal, we will pass the root. If root, in order traversal of root dot left and print root dot data, in order traversal root dot right. So this is the code for in order traversal. To summarize, we have learned about the recursion basics, a function calling itself to solve smaller instances of a problem. Base case and recursive case, essential to prevent infinite loops and ensure correct execution. Classic problems, Factorial, Fibonacci, Tower of Hanoi, binary search and tree traversals. Time complexity considerations. Some recursive solutions can be optimized using memoization or iteration. Some real-world applications used in trees, graphs, sorting algorithms and backtracking problems. So in the next video, we will be learning about the backtracking with recursion. I hope this video helped you understand classic recursive problems. Don't forget to like, share and subscribe to CodeMaster for more coding tutorials. See you in the next video and happy coding.